Yeah, we will be starting with our first session on basics of remote sensing. We have with us a guest faculty from National Remote Sensing Center, ISRO, Hyderabad, Shri Harish P, scientist engineer SF. He belongs to Training, Planning and Coordination Division of National Remote Sensing Center. He has MSc in engineering physics with specialization in photonics from NIT Warangal. Has specialization in optical engineering and worked as optical design engineer initially in manufacturing of optical instruments, and he joined NRSC in the year 2020. 2010. Currently, he is working as a scientist, as I said, in the training division for organizing capacity building programs in geospatial technologies at NRSC, contributing in planning, designing, and structuring the contents and practical tutorials in remote sensing and GIS. His areas of interest are hyperspectral data processing, Earth observations data and applications, digital image processing, geospatial technologies, spatial modeling, and open source tools. So with this brief introduction, I welcome Shri Harish from NRSC Hyderabad to deliver today's first session on basics of remote sensing. We will be having the second session at 3 o'clock in the afternoon, which will again be delivered by Shri Harish. It will be on basics of remote sensing, including map projections. Thank you. Over to you, Shri Harish.
Yeah, thank you, sir. So good morning, ladies and gentlemen. Am I audible to, can anybody confirm?
Yes, you are audible.
Yeah, thank you very much, Chaitanya Garu and all the organizing team from the National Water Academy. So I'm very happy to be a part of this program and also sharing with the participants some of the fundamentals related to the remote sensing and GIS. So as was told in the inaugural session by our chief engineer, sir, so this course is very apt and relevant in today's time, in the current generation, where you see the volume of data generated by from the satellite platform on various platforms is actually enormous. So with that kind of data available, so processing, storing, and also the dissemination of data becomes very important. And to have open source tools like QGIS, it is actually a big boon for the entire user community. QGIS, just for the information of the users, is a free and open source software. So you can do actually a lot of geospatial analysis using the QGIS, and it's a professional and also it has very advanced image processing and GIS tools. So probably some of these things you will be coming to learn in this duration of this 2 weeks program. So my only suggestion will be to kindly go through this some of these technical session and the hands-on session, and especially on the scripting part. So even I find it very interesting that you have included this scripting use of the QGIS with Python. So that will be a valuable addition. In fact, it will be like the best for people with who have a little bit of scripting knowledge and who can customize, who wants to customize some of these tools, like if you want to create forms or if you want to create models. Very interesting addition to this particular training program. So without much ado, let me introduce myself. My name is Harish Vesara, and I'm working as a scientist engineer SF. I work in National Remote Sensing Center, which is one of the major centers of Indian Space Research Organization. So we are situated at Hyderabad, and we also have a campus at GD Metla. So I'll share my presentation probably through some of the slides. I'll also introduce our organization, and we'll go ahead with the discussion on this topic of basics of GIS. So I'm sharing the screen. Kindly acknowledge whether you are able to see it full screen.
Yes, sir.
Yeah, it is taking a while for me. Kindly bear with some of these small interruptions which you may be facing through the network. Yeah, if the slide is visible and the screen is full on,
Yes, it is visible.
I hope there are no blocking of the pop-ups. It is full screen to see.
Yes, it is full screen.
Yeah.
Yes.
Okay. So thank you. Like sometimes, the pop-ups will black some of the content. So yeah, so I'll go ahead. So having come from an organization which is primarily dealing with the satellite data reception, the data storage, processing, and also the dissemination of the data. So I'll take you through some of the fundamentals of the remote sensing. So why remote sensing is needed? What are the various platforms through which we acquired this data? Like what are the the key words and some of the key concepts that one has to remember, especially working in this domain. So this is probably a topic which I think will be amenable to many of you. Okay, so although the design, engineering, the technological part is slightly on the advanced side, but from the application point of view, you see like anybody, irrespective of the background, anyone can come and use the satellite imagery and the GIS and the location-based information, and they can provide solutions to some of the world related issues. Okay, so we'll start. So is my slide change will? Yeah. So as I told you, like the mandate for National Remote Sensing Center is to basically receive the data. So we have our major data reception center at Shadnagar, Hyderabad, where we have the infrastructure, the technology, and also the tools to basically acquire the live data. So whatever the satellite data that is coming from the ISRO satellites and also some of the global satellite is received mostly at our Shadnagar center. And we also have some regional ground stations where we have the facility to acquire some of the meteorological satellite data and also the communication satellite data. So we receive the data, we store the data, and we also disseminate the data to the users. Okay, so we have a very huge user community who are using this satellite imagery. So not only our Indian data, but also the foreign data is, they come in like 24/7 in terabytes of data per day. So all this data in a systematic way is made available to the users. I'll also show you like some of the platform where you can access these data in the coming slides. Right. So we also have separate, domain people, expertise that are using this satellite imagery to provide, geospatial information and applications like natural resource management, urban applications, forestry, agriculture, disaster management support. So there are separate, dedicated people who are using the satellite imagery to, for the various applications. So as you can, remember now satellite imagery usage has become a commonplace. Okay, so even in school curriculum also, people now students are being, asked to prepare maps, point out locations, okay, of the cities, the monuments. So all these exercises probably are now being included in the school curriculum, so that they also get some awareness about these geospatial technologies. Okay, so we have we'll generate like a lot of satellite data products, right? So the products are basically the ready to use satellite imagery for like finding out like where the the flooded areas are there, where the crop is under stress. So all these some of the data products are there related to the landscape, related to the water resources, related to the urban. So various such products are made available. And we also deal with some of the ministries. We deal with the agriculture ministry, the forestry, right, for providing some of the the know-hows or the what do you call the expertise, so that they can also use the satellite imagery for their own day-to-day work, right? So we also have separate, as I've told you, like campus is there at GD Metal Hyderabad, where we also organized capacity building programs, especially for the in-service professionals across the country. And also we have a dedicated student outreach center where you can visit our center and have a look at like what all the activities ISRO is doing in the form of exhibitions and in the form of some visualization tools and all those things, right? Yeah. So next the question comes. So I've structured, yeah. So any queries, kindly. So I request all the users to, I mean, as told in the morning session also, so kindly have some, mechanism where you can post the questions in the chat or communicate directly to the organizers so that we'll have a, smooth streaming of this online session. Okay, so I've structured in a way so that it will be appealing to the people with the background and also who are new to this particular area. Yeah, so the next question is why remote sensing? So why we have to really acquire the data through a satellite, that matter any other aerial platform to know what is happening on the ground. Okay, so we see what we see. Okay, as human beings, when we look around, we see like various features on the ground. We see buildings, we see people, we see a lot of natural features. So then why there is a need to basically acquire the data from a platform that is especially the satellite platform? So the simple question, simple answer to this is like our Earth as a planet or as a planetary body is a very huge surface. Okay, the scale at which it is in a real world is mind-boggling. Okay, so we cannot really see it as a 1:1 scale. So to see it at 1:1 scale, probably you have to travel from other planet, or probably you have to go to the space station to see like the entire globe of it, right? And our Earth is very dynamic. Okay, so because there are a lot of natural processes are there, a lot of man-made activities also are taking place, which are actually putting a lot of stress on the environmental processes or the natural processes of the Earth. We are directly changing the dynamics because of our, the thriving civilization, or you can say a lot of man-made activities that are taking place. Okay, right. So if you have to study the entire Earth as a system, so we need to basically have data. So if we have data only, we can do some meaningful, analysis or interpretation about like what is happening, like what is the state of that surface, okay, or what is the condition in which a particular, let us say, plant is there or vegetation is there, or like how polluted water surface is, right? So this we can do a fantastic job by going to the field. But to get basically what is called as a bird's eye view of what is happening on the ground, the satellite platform basically offers you the great advantage. Sir, I think I've lost my screen share.
Yes, we are seeing some screen. You may try to share it again. Yeah, please share it. Yeah.
Now it is visible, sir? Yeah. Yeah, so the point I was trying to drive home is basically the scale at which we have to acquire the data is, is enormous. So we need basically multiple platforms, basically a constellation of satellites in order to, study our, various subsystems, especially our landscapes, our oceans, our, forests, and basically the impact that is generated by the civilization. So all these things have to be the data has to be captured, it has to be analyzed, and some information has to be generated to make some key decisions. Okay, so how to make the resources in a sustainable fashion, or how to avoid the the floodings. So how to basically phone warn people so that they can they are aware of the risk they will be in. So all these things probably need to be understood in a, from a very large scale to a very micro scale. So that means at a very local level to a very global level. So that's why the need to acquire the data to remote sensing is very much there, right? And very much there. Probably it started with the Landsat program from the early 1970s, and then it actually grew from that day. And ISRO was also was having its own remote sensing program from the year 1995, where we could launch our own series of satellites, resource sat series of satellites to do the acquisition of the Earth surface, right? So that is basically where the need comes for doing the remote sensing. Yeah. So then we have seen, like, over the last 2 decades, we have seen the remote sensing, which is providing you the satellite imagery and also the geographic information system, which has also become very accessible and also available to many users. And the location-based services, probably you're also aware of the location-based services or the systems that are now we are dependent upon for our day-to-day life also. So the convergence of these critical technologies have provided to what is known as the geospatial information. Okay, so geospatial information basically combines the data that we have collected from the remote sensing platform, the data which we have created using the geographic information system, and the location-based, or the coordinates or the position-based data. So if we combine, it becomes, what is known as the geospatial information, which can basically provide you a lot of solutions as far as the problems on the real world is concerned. Okay, so that is the era we are currently in, the geospatial technologies. So now if we combine these critical technologies with the internet or the information communication technologies, where we use the internet, the Wi-Fi, the Internet of Things, the very local devices that basically help you to collect information or to do the surveillance, like how we use the CCTV cameras. So these technologies have now given us the platform where we can combine these technologies for capturing, for processing, for also disseminating, and also making key decisions based on the information that we have generated. So this is what we call it as a geospatial technologies, and now it has become the mainstay of the technologies, especially when you consider these the remote sensing GPS is concerned. Right. So we are also looking at what is known as the ecosystem. Okay. So now we are in an age of startups where, like, we have seen, like, a lot of now the startups or the incubators are coming with very smart ideas of how we can use the satellite imagery, or we can use the location-based information, and also the cloud-based computing. So how we can generate very smart solutions catering to a particular segment of the applications. Okay, so now this ecosystem is also it's very thriving, right? Especially given now the environment in which the geospatial technology is in now. So we have a lot of free data that is available. You have a lot of cloud-based computing platforms. Okay, so you have a lot of open source tools like Python, you have QGIS. Okay. So with the advent of all these things, probably now the startup ecosystem is also very thriving and trying to work out very smart solutions. So what all this basically does is it will, and including the policies and the the governance for the growth of this particular domain, geospatial technologies. So this will ultimately contribute to what is known as the geospatial economy. Okay, so where we have an economic system like that is primarily dependent on the geospatial information, the location-based services, basically drive a lot of sectors. Okay, so either in terms of generating solutions, providing employment, or developing the technologies that will basically help the governments or the departments or the people to basically come out with critical solutions to the day-to-day problems. Right. So with this background, let us quickly go to what we mean by the remote sensing process. So the remote sensing process is what I'm trying to tell you, like as I've told you before also, to go into each of these technologies separately will be, it's a big task. So to simplify this, what we'll do is we call this as a remote sensing process. Okay. So if you see, like, especially when you want to capture the data from a satellite platform. So first thing is you need to have a satellite in the orbit. Okay. So for that, you need to know like the know-hows of the design, engineering. So I'll not touch upon all those things. Let us assume that we all know, like, ISRO launches satellites, the remote sensing satellites, the communication, and also the other navigation satellites. Right. So we have a satellite that is launched in the space. So it is orbiting the Earth from the North Pole to the South Pole. And it is acquiring the data. So here we have two forms of remote sensing. So the slide that I'm showing to you, it is called as a passive remote sensing. It is also called as optical remote sensing, where the camera that is situated on a spacecraft. So imagine that you have a camera in the spacecraft and it is looking down at the Earth. So it is only getting the energy that is emitted by the targets. So where the energy is coming for the Earth, the planet Earth, it is from the sun. So as we all know, like the sun is the main source of energy for the life on Earth, right? So we have what is known as the incoming solar radiation that is, illuminating the Earth's surface and all the targets. Okay, so whatever the features, I'll use the word target, feature, and also the objects interchangeably. So kindly understand that. So once the Earth is illuminated, we have what is known as the process of reflection or the emission or the absorption that is taking place. Right. So these reflected energy and also the emitted energy. So what basically the solar energy does is it warms up the Earth. Okay, it warms up the atmosphere. It also warms up the oceans. So when a body is warmed up or is heated up, basically it also emits its own wavelength apart from the reflected energy. So we have sensors to detect this reflected energy. We call it as a what you call passive reflected energy, and also the thermal energy, which is by virtue of the temperature of the body. So these two forms of energy going back to the camera or the what you call the camera system on the spacecraft. So they will record the data. And once the data is recorded, it is transmitted real time back to the ground station. As I told you, like it will be received here at our Earth station or probably any other center in the country or across the globe. So these Earth stations or the ground stations are meant to receive the data from the spacecraft, especially the remote sensing spacecraft. And once this data is tracked or received, it will be streamlined. So there's an automated process that takes place at our ground station. So it is captured and it is stored in our storage system. And from the storage system, so everything is systematic. So everything is pre-programmed, planned, and systematic, so that we have a record of what we are receiving, what is the area we are receiving. So everything will be tagged accordingly, and it will be stored in a very systematic manner for retrieval and then the pre-processing. So we'll come to some of these, processing and pre-processing terms in the coming slide. So once the data is pre-processed, there will be different levels of data products that will be generated based on the user requirement. So we have a level 0 processing, we have a level 1 processing, we have a level 2 processing. So different processing stages means different forms of removal of the noise or the distortions, or adding some more information to the data so that it will be much more readily interpreted. So all these things are done, and the data will be supplied to the users through some of our dissemination platforms. You must be aware of the NRSC Brunidhi platform or the ISRO Brunidhi platform. Then we have the Bhuvan also is providing a lot of thematic geospatial data. So all these are basically sources where you can get this satellite imagery or the geospatial data, you can download it. Okay, right. So now we'll not go very deep into the definition of what is the term remote sensing. Probably if you refer to many books that are based on the remote sensing, you will see like there's a different type of definitions that is given. But actually, what is the adopted definition is what is displayed on the screen. So that means we are making use of the electromagnetic energy that is coming from the sun, right? So either that is reflected or emitted by the different features on the Earth's surface. So the main purpose of doing the remote sensing from the satellite platform was to to improve the natural resources of the country. So how well we can manage the natural resources of a particular country, and how we can understand the land use patterns or the land cover patterns, basically aiming to the protection of the environment. Okay, so when we say energy, we are actually talking about the energy that is coming from the sun, which is electromagnetic in nature, right? So any radiation, if you take or any frequency you take, it is basically electromagnetic in nature. And when you say electromagnetic, the process, how it emanates is basically because of the interaction between the electric and magnetic fields, right? And then the propagation of the wave is right in the direction perpendicular to this direction of these two fields, and it travels at the speed of the light. Okay. So like once you have, let us say, a camera in this spacecraft, and it keeps on orbiting the Earth. So the main purpose of using the remote sensing camera is to acquire the data from the Earth's surface, okay, and also the atmosphere. And there are various sensors in the coming slides, like how these sensors are acquiring the data 24/7. I mean, not only only the single satellite, but we have a constellation of satellites that are meant for different with different objectives. So one is looking at land, one is looking at the oceans, one is looking at the landscapes, so one is looking at the atmospheres, what is happening in the atmosphere. So we have different constellation of satellites that are actually capturing the data. And the good thing about this spacecraft or the remote sensing satellites is they acquire a different, different levels of detail. Okay, so one is looking at a very specific region at a very high detail. Let us say in megapixel, it is looking like some other cameras are looking at probably at a very wide coverage at a very coarser scale. So all this, the spatial, so that means they are looking at the different details, and also the frequency at which they capture the data also is different. So the main idea is to see that we have a continuous coverage. So that is the main idea of launching this multiple satellite, because a single satellite will be very what we call difficult to acquire the entire globe. So it will acquire, but it will take its own time. Like for instance, if you take the ResourceSat, it will cover the globe in every 10 days. So that means for every 10 days, it will capture each and every portion of the surface in 10 days. Okay, so that means if you have to take the image of, let us say, Pune today, if there is a pass of a particular satellite from the Pune area, so then next for another 10 days, you don't have that particular satellite will again come back only, let us say, in another 10 days after today. So like this, there is a specific repetitivity rate, or the frequency we call it, at which the satellite passes, and we can take the images of that one. Right, so there are regional satellites, there are global satellites. So they are looking, their satellites probably may be aware, like they are put in a orbit, which is looking at at the entire region of the Earth. Okay, so we have the MODIS range of satellites. So like this, plenty of satellites are there that exist that are capturing the data. Right, so the main advantage is, as I've told you, like it will give you a synoptic view of the various various processes, whether it is physical processes, the chemical, biological, which the human eye cannot decipher. Okay, so only through proper examination we'll get to know what is happening. So all these processes are in fact captured by the camera or the various instruments that are put in the spacecraft. And the main idea is to, as I've told you, like we need to examine, or we need to study, or we need to analyze, we need to process from the satellite is happening. Okay, so there are various forms of interpretation which I'll show you in the coming slides. Okay, so apart from this, these satellites, what they help is they help the analysts, the scientists in this domain to track the changes. So what is happening, at a various scales. So what is the condition? What is the state? Why a particular, let us say, a landslide? Where the landslide has happened? What are the factors that have caused that landslide? Whether it was a natural or it was a man-made. So all these situation on the ground can be understood. Okay, so I'm not saying like it will give a foolproof picture of what exactly has happened, but it will help the scientist or the analyst or the decision makers to arrive at certain facts that will be helpful for taking some decisions. Okay. Yeah, so there are two different forms of remote sensing. One is the passive remote sensing, which is also called as optical remote sensing. And then we have what is known as the active remote sensing, where the spacecraft will be equipped with a source. Okay, so just like if you have let us say a laser or a torch with you, so you can hit if you can hit any target and you can sense what that particular target is. So like this, there are frequencies or the energy bands that are available in the electromagnetic spectrum that can be used to basically send these high energy pulses towards the surface and capture the backscattered or the reflected energy coming from the different targets. Okay, so this is called as the active forms of remote sensing. So we have the synthetic aperture radar, which is basically dependent on the microwave frequencies. We have the light-based frequencies also, and other microwave frequencies that are used in what we call as a scatterometer. Okay, so it will basically sense the either the change in the location of a particular particle, or like for if you want to estimate the wave patterns of the oceans, or the wind vector velocity or the direction, the scatterometer is something that is used. Okay, and another thing with the remote sensing is you can capture in a very broad electromagnetic band. Okay, so we can capture in visible, we can capture in the near infrared, we can capture in the short wave infrared, thermal, in the microwave. So all these things probably in a glance I'll try to. Yeah, so this is the constellation or the infrastructure that we need to have in space, so that we can capture the various aspects of the Earth as a system. Okay, so what we are seeing is basically the dedicated satellites that ISRO has in space. Okay, so for looking at the natural resources, for looking at our the cities, the urban towns. Okay, so this is used for urban planning, for the infrastructure planning, for the disaster planning, right? And similarly, because our ours is a subcontinent, we are surrounded by water on three sides. What is happening in our waters also we need to understand. So that is taken care by our OceanSat series of satellite, right? So we have our own infrastructure as far as the weather and climate is concerned. So we have the INSAT series of satellites. So the whatever the IMD issues forecast is based on the INSAT series of satellites. So we have imager, we have a sounder that are basically looking at the weather system of the subcontinent. Okay, so we have a very a big infrastructure, very big constellation of satellites for doing the space observations, right? So this is what I told you, like we can observe from a very global range or a very coarse range. That means we can look at the entire national scene. So what is happening at a national level, especially from a weather point of view. And we also can zoom in to a particular city or a town and see what is happening with the help of the satellite imagery or the data. Yeah, so quickly, like what advantages you get? You'll get global coverage because these satellites are equipped with cameras that are looking at a very broad footprint of the, the Earth's surface, or let us say our subcontinent. And they also have the ability to look at a very small portion. So we can look at let us say an area of 700 by 700 kilometers. And we can also look at a small area like 10 by 10 kilometers from the satellite platform. And we can also, watch what is happening in our borders, in a strategic locations or the our neighbors, what is happening in our strategic zones. So all these inaccessible areas, highly rough terrain or inaccessible terrain. So we can image those areas from the satellite platform. Okay, so there is an international space treaty that allows nations to basically capture the images of their neighbors, or for that matter, any other country. So as long as you're abiding by that international space treaty for outer space usage, I think we can very much image the other countries' data also. So that is how we basically watch what is happening in our, in our border areas or the, the surroundings areas with the other countries. So it gives a bird's eye view. That is what we call as a synoptic view. So it will give a very huge information in a very, in a small frame. Okay. So the frame may be, let us say, some 1,000 by 1,000 lines, but the amount of data that you get in that frame is very valuable. Okay. So multi-scale observations is what we call, like you can, as I told you, from a very national level to very state level to district level. So what basically based on the purpose of your using the satellite imagery, we can we have different scales of observation. Scale means basically like in comparison to what is in comparison to the real scenario, like what is the size of the target you are looking at. Okay, so we call as global scale means that means you are covering the entire let us say the entire Indian nation, or at a very local scale, you are only observing the cities or the towns. So a very broad use of spectrum is there. That means from visible to the near infrared, this we have already discussed. And the frequency of observations or the repeativity of the satellite data is what helps the scientists to track the changes that are taking place. We can use it for change management. So this is especially true in in a developing country like us, where we need to frequently look at the changes that are taking place in our landscapes, to our natural resources, and to a sustainable planning, so that we can remove the negative effects of any such bad planning, right? So whatever the data we get from the ground station is real time. Okay, so also there's a provision where you can capture the data at some other ground stations, so we can get the data real time. That means there is what is called as a turnaround time. So within a span of 1 or 2 hours of the pass, we can get those imagery. We can provide that imagery to let us say the users or the departments who are in need, especially for the in an emergency situation where the need to have look at the data very quickly. Okay, so and the best thing is like it is in the digital format. So once you get the data, you immediately start using the data, right? And you can make your assessment of what is happening on the ground, right? So this satellite imagery is used for a lot of thematic mapping. Okay, so we can develop what is known as a land cover map, forest map, crop map, and a disaster, a map. So many such maps are already being prepared by using the satellite data by various users from different backgrounds. Okay, and also to address the emergency situation, right? So we can prepare like a lot of disaster or the flood inundation maps or the flood hazard atlases. So all this information was prepared with the help of the satellite imagery. Yeah, so there are different types of sensors, as I told you, like the scale at which we need to study the Earth as a system is very huge. So we need basically constellation of satellites, not only from ISRO, but from across the globe, to basically capture what is happening at different in every nook and corner of the Earth as a system from a climate point of view, from an environment point of view. I'm not only saying about our own country, but from a climate point of view. So we need to capture the data in different forms. So there are basically images which will give you a picture of what is there on the ground. For instance, plain satellite imagery. And there are instruments that basically they do profiling. So we call them as radiometers. Try to understand what are the changes in the reflected energy for a given interval of time. Okay, so especially like if you see, these are also called as sounders. So the sounding instruments or the radiometers, so they basically try to find out the changes in the fluxes. Okay, like what is the change in a particular column of the atmosphere. So these are mainly used for the atmospheric profiling, and they'll try to observe these changes in a given interval of time. So those are called as sounders or the non-imaging systems. And then we have the images, which are basically give a picture of what is there on the ground, right? So in a way, we can say like a satellite image or an optical satellite image is a factual record of a particular area of the surface of the Earth, okay, on a particular day. And you get this data, day in and day out basis continuously with respect to the, the type of satellite it is, what is its objectives, what are the different specifications. So all these things, if you know, you can know like what kind of data you can expect from a particular satellite camera. Yeah, so again, this is slightly again, just to give you a broad idea of the type of scanning systems that were used to capture these data of the Earth's surface. So this is one is called as a whisk boom, which is basically pixel by pixel, and then we have the push broom. So this is just to tell you like the imaging from a satellite platform or aerial platform is different to what we do in our day-to-day lives. Okay, so now the mobile camera being a very a very commonplace right now. So that is basically it's a frame camera, and the sensors or the small chips that are provided to basically capture this energy are different to what we use in the spacecrafts. So these are actually space grade cameras. They are designed, engineered in a very lab conditions. They are calibrated to function in terms of their performance, in terms of their radiometry. So all these things, and they need to go to undergo this different stages of testing, evaluation, and reliability before they are put into the in a spacecraft. Okay, so now the push frame scanning is the most preferred way of scanning because it captures the data in a much more reliable fashion because we have what is known as the dwell time, which is again a factor that will affect the quality of your imagery, right? So this is a small example, but again, as I told you, like this is I'm just trying to give you a broad idea of what is happening. Okay, I think this is already we are covered. Sorry for the repetition. Yeah. So especially the passive remote sensing satellites, we have what is the the very thick layer of atmosphere, which is in fact is a source that will is protecting us. So we are safe on the Earth because of this very thick layer of the atmosphere. But from a remote sensing point of view, it is a small hindrance. It's not a very big one, but it's a small hindrance. So that needs to be understood in terms of what is known as the transmission windows. Okay, so because we have a lot of gases in the atmosphere, a lot of water vapor, a lot of aerosols. Okay, so the atmosphere, as you see, it is not it behaves differently for different wavelengths. Okay, so for some wavelengths it is opaque, for some wavelengths it is transparent. So what the remote sensing domain person will do is he will basically understand where are these channels. So we call them as atmospheric windows. So you can see in both the visible to the visible to the short wave infrared, that is from from the 0 to 30 microns, and also beyond 30 microns. So there are different channels in which the remote sensing, a particular frequency has to be designed in such a way so that we are getting back the information that we are capturing. So that is the main idea of using this remote sensing windows or the atmospheric windows, where the passage of light, it is affected to a certain extent, but not very big as compared to other wavelength regions. Okay, like for example, in this slide, if you see, so there is a good transmission between 0 to up to 1 micro meter. But if you see like the 1.3 and also the 1.5 channel, so there is a big attenuation of that transmission. So like this, there will be some specified channels or regions of wavelength that we need to understand, and only we need to design the sensors so that we can capture the faithful reflected energy coming from the surface of the targets. Okay, right. So just is again just for information, like how the energy spectrum is present in the nature. It is continuous. It is having a very high frequencies. It is having very low frequencies. The type of energy on the frequency you want to use is dependent, as I've told you, like what is that you want to image, whether you want in the visible region, like how we do with our mobile cameras, or if you are looking at certain properties of a feature, let us say vegetation or a mineral, which has a different specific properties related to the absorption or the reflection based on the wavelength and also the composition of that particular material. Okay, so based on this, we will try to design the the cameras or the sensors so that we can capture the reflected or the emitted regions. Again, this is one more slide telling you like where these absorption windows are there. So wherever these white big valleys are there, right? So these are basically your absorption windows, and you cannot observe the surface features. That means the data that is coming or the signal that is coming from the surface features in these regions from a space platform. Probably down back on the earth, you can use any ground-based instrument to capture that information, or probably slightly highly elevated. If you are using aerial or a drone platform, you can capture it, but not from a space platform, right? So again, there are different sensors that are given here. The optical land imager from the Landsat, and then enhanced thematic imager, mapper. So these are basically some of the global satellites which follow these atmospheric windows, right? Yeah. Yes, sorry. So I'm using this mouse to scroll through. Yeah. So one also need to understand, especially as I told you, like this is a field that anybody can start working, provided they know like which satellite data to use, like what is the problem that they are trying to solve based on the imagery and also the GIS data. But especially if you are a domain background person, like if you are a agriculture scientist or a soil scientist or a water resource person, you need to go a little in depth into what is known as the factors that are affecting the vegetation, what are the factors that are affecting the soil, what are the reflective factors that will affect the water, the surface water, or let us say water that is slightly having different sediments or contamination. So all these things can be studied, but to a certain level, not 100%, but definitely this from the satellite imageries, many studies have been reported that we are looking at the stress that is affected on the crop, how the forest have been affected by the what you call the the deforestation or the rainfall. So such studies are there for the in the public domain. You can go through. So we need to the people who are working in this particular background, they need to go in depth with the go into a little bit of science. They need to understand what is known as the reflectance properties of different materials, see where it is getting absorbed more compared to its normal reflectance. So all these things in detail, our scientists will go and will try to examine what is happening on the ground directly from the imagery. Okay, so they'll take also some help of the ground-based data also in order to collect some relevant information related to their analysis or the study. Okay, right. So the technology, remote sensing technology, as I've told you, like as a user, especially as a person working in this background, I need to only worry about the data. Okay, But you see, like you need to have this entire infrastructure. Okay, so to put a spacecraft in space, basically needs a lot of capability in the space sector. So you need to have the launch vehicles, you need to have the rocket technology, you need to have the satellite technology, you need to develop space grade instruments, cameras, the communication systems. So all these things probably you need to develop this capability, and ISRO is one of the nations which has the end-to-end capability as far as the space technology is concerned. So we develop our own rockets, we develop our own spacecrafts, and we launch our own satellites and get the data from these satellites for our user community, right? So once you have this data, you can see like there are a lot of open source tools and also the license tools that will allow you to display the data, to analyze this data, extract information from this data, and use that information to arrive at certain solutions that will help to solve the problem on the ground. So as I told you, like with this data, you need to go a little deep if you're trying to quantify like what is happening on the ground directly from the imagery. You need to go a little in depth, be a soil scientist or a the person working in the agriculture or in the emergency management, disaster, or the mineral mapping or the water quality mapping. So all these things need to be understood in detail. So we need to go for that type of analysis. Okay, so this is an example of a satellite imagery, and you can see here with the help of this satellite imagery, we were able to derive certain maps, and these maps are used to prepare what is known as our national inventory of natural resources. Okay, so this is a project that we have done for the last few decades we have been doing, and this will basically tell you like how the land cover. Okay, so that means if you map the each and every pixel to a particular class. Okay, so one pixel, let us say of 56 meters in size. So if you map like a land use land cover map, we'll get it, and how the land cover has changed over the last decade. So all these analysis have been done. So that is basically the main idea of using these multispectral satellite images. Okay, so there are various platforms through which we can acquire the data, as I've told you, but the platform that is a satellite platform, the way you can collect the data, the way you can cover the data is unmatched. Okay, so that means satellite data is basically the optimum way of collecting the imagery of the Earth's surface. But you see, like the other forms of other platforms are also now become very, very handy. Okay, so very, now especially with the drone and the UAV platform. So you can plan like a particular area coverage capture. You can capture it. You can retrieve the data, and you can start your analysis very quickly. Okay, so these are some of the platforms. So yeah. So like every remote sensing satellite will have its own or track that is called as a orbit. Okay, so this is basically the path followed by the spacecraft in space around the surface from surface of the Earth in a north pole to the south pole. So this is basically one example of what you call as an satellite orbit, right? So based on the objective of the spacecraft, as I've told you, like it can look at a very small strip of the surface of the Earth, or it can cover a very large portion of the surface. We have global satellites that are looking almost. You'll get a disk, what you call the Earth disk, no, which will give you the hemisphere of the Earth. So like MODIS and also the Aster type of satellites. So though they are looking at a very broad, picture of the Earth. So there are local satellites also that are looking at a very specific region of the Earth. Okay, so everything is is a programmed way. So this the orbit the satellite takes will be programmed in such a way it goes in that particular orbit only, so that we'll have a systematic coverage of the entire globe. Okay. So the orbit is basically that path that is imaginary path that is being followed by the spacecraft, and the swath is basically the size of the strip. Okay, so once it starts capturing from the as it descends from the north pole to the south pole, the swath remains constant, or the coverage remains constant. So when in the land portion, the camera is switched on so that it will acquire all the land portion. And when it comes to the ocean region, so it is switched off, especially for the ResourceSat series of satellite. But oceanographic series of satellites, so they have different instruments that are looking continuously at the ocean surface. Okay. Right. So again, there are various types of orbits. I'll not go into detail. Right. So we have, we can observe this Earth from various orbits. So this is called as geostationary. Then we have a geosynchronous. So mostly the remote sensing is done from the polar orbits. Okay. So we have what is also known as a polar sun synchronous orbit, which I'll show in the subsequent slide. So the Molniya orbit is basically for regions which are high latitude regions. Okay. So especially like Russia, if you see, it is very close to the North Pole. Okay, so they don't have the benefits that you get from a equatorial country like India. So they rely on what is known as a highly elliptical orbit that is called as a Molniya orbit. Okay, so they have like a series of satellites which will be put in this particular orbit. So the visibility, as you can see here, because the apogee is very large for this particular orbit. The high latitude countries like Russia will be in visibility of that particular spacecraft. Okay, this is used for again for communication, but you can do a little bit of image capturing also from that particular orbit, from a geostationary orbit also. So geostationary orbit or the geostationary is used for the communication purpose, and for our all our meteorological satellites are geostationary. Geosynchronous orbits are used for the navigation purpose. Okay, so this is what happens in a polar sun synchronous orbit. It is called as polar sun synchronous because the tilt of this particular orbit is in sync with the rotation of the Earth across the sun. Okay, so this is the main advantage that you get with this polar synchronous orbit is you will have uniform illumination. That means the sun will come at the same angle in that particular region on all the 365 days. Okay, and this applies to each and every region of the surface of the Earth. That means the illumination conditions will be normal, so that we can compare the images, the different images of that particular area very easily. So that is the main idea. But again, because of the weather conditions, there may be a changes in the day-to-day cloud coverage or the situation of the ground, like the pollution level. So all these factors will affect the remote sensing data that I'll show you in that remote sensing data chain. So this is a brief. The Earth is moving from west to east. That means rotating from west to east, and the polar remote sensing spacecraft is orbiting the Earth. Okay, right. So some background again to equip you like for this particular course. Then again there are like some major characteristic that one need to understand about the data that you're getting. Okay, so as I told you, like the volume of data that you're getting now is very huge. So we need to understand basically what is the data you're looking for. So before you go to a particular data, you need to understand what is my objective. What is the reason you're using the satellite data? So probably these are very, very plain questions that each one of you will get, or the thoughts you will get. Based on that, you can decide like what are the type of characteristic or what type of specifications you want from the satellite data. As I've told you, like there are different types of satellite imagery that are already available, right? Yeah, so first one is basically like in how many channels you want, whether you want a multispectral or you want a very, very narrow range of bands placed closely spaced, like what you get in hyperspectral. So the multispectral is what is mostly used by our, land use, land cover scientists, the urban scientists, the urban people. Okay, the emergency management, the planners, the infrastructure people. So they are mostly, they look for the multispectral data. And especially for the science people, so people who are working in the, in the scientific projects, like they want to quantify certain, for the mineral exploration, mineral mapping, or the water quality, or the crop stress level. They want to quantify it. They want to exactly specify what is happening on the ground directly from the imagery. For such people, we have the hyperspectral data that is available. Okay. So here is like there are very close range bands are there from 4 to 2.5 micrometer regions. Okay. So again, these are given in the what you call the wavelengths. Okay. So for these are called as a broad band sensors, multispectral are also called as broadband sensors. And then we have the hyperspectral sensors. As I told you, like for mostly for science applications, we use this one. Right. So this is called as a spectral characteristic of the data. Then we also look at what is known as the pixel size. So pixel size means the level of detail that you are getting from the satellite imagery. So whether you are looking at the what you call the buildings. So you want to know like what type of buildings are there, what is the road infrastructure in that particular area. So based on the levels of detail, you can go for high pixel size. That means you'll get almost 1 meter pixel size or better than 1 meter from our CATO series of satellites to almost 250 meters or 180 meters pixel size. Okay, so in a simple way, with the pixel size or the spatial resolution can be understood by comparing the pixel size given by the sensor in terms of the area occupied on the ground. Okay, so when I meter means like it is capturing the region that is 1 by 1 meter on the ground as a 1 pixel. Okay, so we all understand like now digital images means it's a bunch of pixels. So that data is basically captured, that is 1 meter or the 5 by 5 meter or the 10 by 10 meter data is captured as a single pixel. So whatever the information that is, of that size or smaller than that size, you will not be able to discriminate that better. That means you need to go for a better resolution to see what exactly is there on the ground. Okay, so this is basically nothing but the pixel resolution or the spatial pixel size or the spatial resolution. Okay, so then we have the radiometry. As I told you, like we need to also quantify the different shades that are possible in a camera. So just like your day-to-day camera, we also need to specify like how many shades it can capture. So the better the shades it can capture, the better your discrimination of the targets can be made. Okay, so it has a direct bearing on what is the type of analysis you can do, what is the type of feature extraction that you can do. So these radiometric, range is generally given in terms of the bits. Okay, so that means like how many values of zeros and one that you can fit in a single for a single pixel value. Okay, so the higher again, the better your discrimination or the differentiation, but it will also consume a lot of space in your Okay. Again, temporal means like what is the frequency or the repeativity of the spacecraft, so that we can capture any any emergency event very quickly. Okay. So the higher the repeativity rate, so there's always a trade-off. What I'm trying to tell is like when your coverage is very huge, okay, so you have a very good repeativity, right? Because we are covering a very broad footprint of the surface area. We can see like what is happening there very quickly. But typically, if the coverage area is less, then your repeativity also will increase. Okay, so we have satellites, as I told you in my initial slide also, that are looking at on a basis, that are looking at a day basis or a diurnal basis, weekly basis, fortnightly. So all such type of repetitions are there. Okay, right. So the main advantage. The main idea of giving this slide is again to show you like how these characteristics will help you to decide what type of data you want. Okay, so if you are an urban planner, so you need basically high resolution data. Okay, because you're using planning activities, so you need to see the delineation of the roads, the edges of the roads, the buildings, so that you can plan effectively. But if you're a resource person who is working on, let us say, the water, okay, so you're looking at a particular catchment or a watershed. So you need to basically have a broad coverage area so that you can find out like what are the different zones that come under this catchment. Okay, so whether there's a small hillock is there, whether fields are there, or whether the terrain is highly undulating. So to study such aspects of the terrain, you need to go for a slightly coarser resolution. Okay, so basically what type these characteristics will help you to decide on that one. Okay, so whether you're only doing a simple thematic mapping or you're doing a deep analysis, so that will again your radiometry comes into picture. So based on these characteristics, you can take a call of what type of satellite data is useful for your study or analysis of the your imagery. Okay, so this is probably in a nutshell like how the remote sensing data starts its journey. So once the satellite is, operational, it will start acquiring the data. So then, there is what is known as the that is mostly like related to the signal processing. Okay, so it is not based on image processing. So there is a level 0 processing that basically will basically separate the signal from the the carrier, and also it will decode the data. It will decrypt the data so that it comes into a digital form that is easy to read and basically store the data. So that is a level 0 processing. But the pre-processing is done basically to correct the distortions. Okay, so because you're capturing the data from almost 600 kilometers, 800 kilometers, so there will be a lot of distortions because of the atmosphere, because of the movement of the spacecraft, or because your camera is sometimes does not work as expected. So all these errors are corrected in the pre-processing level. And once this pre-processing is over, like we'll correct for the line dropouts. If there, we'll do the atmospheric correction. We correct what is known as a geometric correction. We call this as georeferencing. So all these things can be taken care in the image processing stage. And once the fully corrected data is done, then we go for the post processing. So where the users work with the data. So they take the data, they go visualize the data, they interpret the data, they will do the feature extraction, they will convert the data into information, they'll convert into maps, they can use for for using in a decision support model. They can do some use the different machine learning techniques to give a more reliable data out of that one. So all these things are basically the post-processing operation. So where the spectral classification or the textural classifiers. So a lot of things are there. Probably you'll come across some of these in your coming sessions of this training program. Right. So again, this is just for your information, like what are the main focus bands of the multispectral sensors that we are doing. We are using the visible band, that is a blue, green, and red. Then we also have the infrared and the short wave infrared. Okay, so the infrared and short wave infrared are basically to examine some of the properties which are very critical, especially for the vegetation, soils, and the minerals. So they have some of their what we call the diagnostic properties, diagnostic absorption we call it. So they are very they occur mostly in this region, short wave infrared, and also in the thermal region. Anyway, thermal, we have separate channels to acquire the data, but mostly for the land cover mapping, and also to understand some of the properties of the land cover features like soils, crop, or mineral quality. We can use for understanding those properties. Okay, right. So this is typically how multispectral data looks like. If you visualize them separately, probably in the new session also, you will have a chance to work with some of the sample data. So you can see here, like these are the visible bands, B1 to, so they are simple. The nomenclature is very simple. B means band. Okay, B1 means it's a first band. First band basically starts with the visible, whether it could be blue or it could be green. Okay, so B2 again, like, so there's a very simple nomenclature that is very easy to understand. Especially because the data is captured by various agencies. Okay, so we have USGS, we have ESA is there, we have also the Japanese Space Agency. But the nomenclature is very simple to understand and also work with those data sets. Okay, so we have B1 is basically for this particular sensor, which is a list 2 sensor. It starts with the blue, green, red, and near infrared. So B4 is near infrared. So the main, probably the point I want to just stress here is we look at the variation of the brightness values. So see how the images features are changing from B1 to B4. You see, like the portion that has started looking dark for you in the B1 has now suddenly become bright in the B4. Okay, so these are the what you call the changes. The analyst will be interested in to find out like what are the features that are representing. Okay, for a plain eye, probably we are conversant with the various satellite imagery by now. we can tell like this is ocean, this is, this is land, and like some of these green portions of the image are basically vegetation. They correspond to vegetation and all those things. But beyond that, like if I want to go like what type of vegetation it is, what type of, whether it's the trees are there or cultivation is there, or it's a different, there's an separate, ecosystem is there, like mangroves, or where there's yes, all these, if you want to examine, if you want to study, we need to go a little in them. So accordingly, we choose our bands and then we proceed with your analysis. Okay. Right. So again, this is an example showing of how you the spatial resolution or the pixel size basically affects your details, level of details or the interpretation skills. So as I've told you, like the higher, the smaller the pixel size, the better your details. That means you can see a lot of things with clarity. And you can form an first-hand information once you look at the images. Okay, so then by using some with the help of the software tools or the machine learning techniques or the algorithms, we can derive all those features from the satellite imagery. Yeah, so we can derive a lot of information from the satellite imagery. As I've told you, like these are called as image band-based analysis. So you can simply combine these bands in a specific way. And then we can derive what is known as simply the image-based indices. Okay, so NDVI here stands for normalized difference vegetation index. So like this, dozens of indices are there. Probably, I think some of them will be covered, hopefully, in this particular training program. So how we can quickly estimate where these pixels are located in the image by using a simple image-based equation. Okay. So just like how we use a plus b by a minus b or a by b, some ratios or normalized functions, the same can be applied on the images and we can derive some useful information. So this will give you like a first-hand information of where your pixels are located. Okay. But again, to assess what values they have, what they indicate on the ground. So again, it's a different exercise. Okay. So, but we did, these ratios will definitely help you to quickly highlight those pixels. And you can further examine these pixels in terms of their value, in terms of their location, in terms of their category. So all these things can be understood on a later stage. So this is the satellite imagery, color composite imagery on the left side. And using this imagery, we can derive what is known as a simple thematic map. Okay. So by the process of classification. So image classification, I think you might have heard this term on multiple occasions. So image classification means we are converting the pixel value to a particular label. Okay. So especially if you have a multispectral band or a color composite band like the one on the left, which is showing you the false color composite. FCC means false color composite. It is a combination of the different channels of the multispectral satellite data. So we have, as panchromatic data, and we also have the multispectral. So this is an example of a multispectral data where you can compose an image and convert that image using simple classification techniques. Okay, so we have standard classification techniques like supervised. Then you have advanced, like you can go for what you call for random forest. You can go for decision-based classification. So multiple such techniques are there. I think they are already implemented as an interactive tool in QGIS. So probably if you have one of the sessions on supervised classification, you will get to know how we can convert these multispectral imagery into a simple, land use land cover thematic map like this. I think that will be that you can explore. Yeah. So now coming to the active form of remote sensing, which is also called as a microwave or the synthetic aperture radar. Okay. Right. So this is called as the active form of remote sensing, which uses its own energy pulses rather than relying on the sun as a source of energy, which the optical remote sensing does. The active remote sensing uses its own source of energy. So especially in the regions where there is a high transparency of these frequencies through the atmosphere. Okay. So generally the microwave region, that is from 3 gigahertz to 30 gigahertz. Generally, that is mostly transparent unless you have a very thick cloud cover. But otherwise, mostly these frequencies are transparent and they can easily penetrate the cloud, and they can also penetrate the aerosol position of the atmosphere. So they'll go So this is also called as day and night imaging. So you can operate a SAR any time of the day, whereas for the optical region, as you've seen, like it has a particular equatorial crossing time. Okay, so that is decided around between 9:30 to 10:30 p.m. Depending on the position of the satellite and also the orbit and also the altitude. So between to 9:30 to 10:30 a.m. that is in the morning. So we have daily passes of the optical optical satellites. Whereas for synthetic aperture radar, like the microwave, it can operate 24 by 7. 24 by 7. So whenever you switch on the camera, it will take the images. Either you can transmit it real time, or you can store it in the onboard storage, and then you can retrieve the data. So there's a clear comparison you can see here, like how the cloud is hindering your view of the surface. You can see there's a lot of cloud pixels, and this image was taken during a high rainfall incident, right? And you can see a lot of cloud pixels that are scattered around. Whereas the same image that is captured from the microwave sensor, it can see it is clearly showing you the terrain information. Okay, so you can clearly see the river courses, like basically all the flood inundated pixel or the water inundated pixels are highlighted in the very dark color. Okay, so all these regions just by the side of the river course are giving you the all the flooded areas because of the heavy rainfall that has happened in this particular region. So in such situations, the SAR, that is a synthetic aperture radar, will be very useful in capturing that information. Okay, so it is also called as day and night information. It is also, it will weather resistance also in here, even during high weather conditions also, especially in a cloudy conditions also, you can capture the data, and you can operate the sensors any time of the whatever the window you have. Okay, so irrespective whether it is day or night. Okay, right. So this is how the principle works. Again, it is a principle of capturing the echoes. Okay, so this is again based on the radar. That means you find out what is the time delay between sending of the light and receiving back the scattered or the reflected energy, and you try to estimate the distance. So this will give you the distance, but actually this is an imaging sensor. So it does a lot of signal processing, which I'll not go very deep into. So just like for the example sake, now I think you are having mobile phones that also using the LiDAR technology. Okay, so it has come in Samsung and also in iPhones. We can just basically point your camera at a particular target, and then you can see that target in 3 dimensions. So that means it is capturing each and every point of reflected point that is coming from the surface of the target or the shape of the target. So in again combining these the Doppler techniques and also the time delay techniques in receiving the signals, it is able to get the correct location of that point in space. Okay, so that is how this technology works. Again, as I told you, like the main point is to do the 3D imaging. So it will also give you the surfacial information, and we can also get what is the basically the texture and the surface properties of a particular target. Right, again, so this is one more example clearly showing you like the difference between optical and microwave imaging. Okay, so the image on your right is basically the microwave image. The image on the left is the optical image. You see like all these small cloud pixels are not there. And you can also see, interestingly, the surface wave profile. Okay, so you can see a lot of waviness in the image that are indication of how even the surface waves can be captured. Okay, from the synthetic aperture radar. So you can clearly see the terrain information and the various features on the terrain. Right, so all these things can be captured, and wherever there is signature of the water is there or the water body is there, all these things are captured as a dark targets. So one more example, like how in a emergency situation, the SAR data will provide you valuable surface information that you can clearly see here. It is clearly showing you the inundated patch just to the down the south of your image. You can see this dark, very big dark region is that inundated portion. Okay. So this is used a lot in the disaster management activities. right? Yeah. So the SAR is again it is a synthetic aperture radar. It is always side looking. Okay, so it is not like nadir looking, just like how you have in the aircraft radar. So aircraft radar is only a time ranging instrument, whereas a synthetic aperture radar actually is an imaging instrument that will also give you the surface details. Okay, so that means the properties of the surface, what is the texture. So all the inferred from the SAR data. Okay, right. So there are simple techniques where you can find out like how the data is acquired. Again, I'll not go into the details. This is just for your information. Like because it is slightly slide looking here, the range resolution is dependent on your the pulse duration. And this is what we call as the across track resolution and the along track resolution. So this being a radar, this is in principle, it's a radar, but it's an imaging radar. Okay. So here the size of your antenna comes into picture, your wavelength of operation comes into picture, your pulse duration. That means the frequency at which you are pumping these pulses into the space. So that also basically affects your resolution, and it will impact your pixel size. Okay. Yeah. So this is the principle of working of the SAR. It works on the Doppler signal processing. Okay. So the same target is captured from the start of the acquisition till the time the object is in the field. Okay. Whatever this energy is pumped towards that particular target are received by the target, and the energy is backscattered. So till that time, because the object is in the field of view, you will get typically a very high spatial resolution from the SAR. Okay. Um, so that's the main principle of operating this SAR. Compared to your optical, it is very straightforward. It will just capture the light energy pulses received from the target, and it will form an image, right? So these are some of the for your understanding. So as you see, like the higher the frequencies, you have, as I told you, like from 3 centimeters, from 30 centimeters to almost 1 centimeter. We have the wavelengths and also the frequencies, like from 0.3 gigahertz to almost 30 gigahertz, 40 gigahertz. We have different channels in which these frequencies are used to image the surface of the Earth. Okay, again, why different wavelengths? You can see here, like, so they have the specific properties of penetrating the surface, especially SAR frequencies they can penetrate, so that we will know like what is the subsurface information based on the backscattered output that is coming from that particular region. So we can go little bit subsurface, not very deep, but at least I mean, as far as the studies are concerned, we can go up to 1 meter or better, sub-meter up to depth of 1 meter, sorry. We can study like what are the properties. Okay, so how much soil moisture is there, like what are the different minerals are there, what are the mineral content in that particular soil, water content, moisture content is in that soil. So all these various properties of the land features can be understood by properly analyzing and also processing the data. Okay. So there are some distortions. Probably this I've added only for your information because it is an active sensor. You will see always the image is very noisy and grainy. You will see a lot of grains in the previous images also that I've shown you. You will see a lot of graininess in the image. You will see a lot of black and white spots that are appearing in the images. So working with this data is always is a challenge because of the noise that is present in the images. But again, we have techniques that will filter out all this noise and will give you the correct information on the ground. Okay. So there are certain distortions like because of the geometry or because of the imaging geometry or because of the terrain geometry that we need to understand. But again, there are tools that will help you to recover the original data from these distortions. Okay. So again, one more view. I think some slides are probably repeated. So like with this, types of data available, the optical and the remotes and microwave data available. So what is basically what we are trying to understand from a national standpoint. Okay, so we can see here like these data sets are used for national projects that are looking at the food security, water security, and also the infrastructure, the energy. Right. So basically, we are dealing with like many projects directly. Either we are hand-holding the ministries, or we are directly interacting with them and providing the expertise or the solutions for some of the projects with the help of the satellite imagery. Okay. So the main idea is like how we can use this effectively on the ground and see that we improve the situation on the ground for the sustainable development, and also some of the governance and the protection of environment and the natural resources is concerned. Okay, so we are looking at natural resources, especially the rural development programs. We are working with the rural development ministry for their watershed development activities, for groundwater recharge development. Such type of activities are there. I'm not coining the words correctly, but we are already doing that one. Okay, so especially for the geophysical parameters of soils, of vegetation, crops, the forest. Okay, and also a lot of data analytics based on this satellite imagery we are doing. Okay. So main idea is how the satellite imagery or the remote sensing can be used for the national development programs is our main focus. Okay, apart from that, we also do a lot of, we have separate, areas that are looking at, water resources or agriculture. We are looking at, we have a separate urban infrastructure management, forestry group is there, geological, sciences group is there. So various groups are focusedly looking at particular aspects of the satellite imagery, and they are developing a lot of information, data layers that are that can be used for addressing a particular field problem. Yeah, so as I told you, like in the morning also, this is a good time to work with the geospatial platform where we can use a lot of open source platforms are there. Google Earth Engine, I think, is very popular. And it's very powerful also to use. So we can use it's a actual one-stop solution, especially working with the satellite imagery. And it also provides a lot of computation facilities and also storage facilities that you can use it to derive the data and also share it with the user community. So similarly, there is a Sentinel portal is there where you can download a lot of high quality multispectral data or the microwave data. Okay, Open Data Cube. Some of the things are listed here. I'll not go through by name. And especially there are platforms that will help you to work with the big data. Okay, like GeoDPP is there. Similarly, the Amazon web services also there, where you can actually subscribe and you can use this computational facilities or whatever the tools that are present there to arrive at some of the information out of the data satellite imagery. Okay. Yeah, so we have a dedicated, Buniti platform where you can actually browse and download the data, and you can also place the data if you're in need of high resolution data. So again, this is will cater to the user requirement based on the new geospatial data. Meter data, it is freely shareable, irrespective of who is purchasing. I mean, this is applicable for the Indian nationals only, right? And also the Indian companies. So you can browse, download the data up to 5 meters free of cost, but anything above 5 meters, probably it has to be routed to proper channel so that you can get access to the latest data to your department or your company directly from this platform. Okay, so we can explore some of these portals due to the, limited time we have. Probably I cannot show you like how it works, but definitely it's a very user-friendly portal that you can go through and you can browse and download the data. Okay. Yeah, so these are some of the slides. Again, I'll not go in detail. You can explore. I'll give you the slides. Even for the elevation models, also there are a lot of open platforms or open resources are there where you can quickly download the data. So there are plugins also, I think, in the QGIS that will help you to access a particular digital elevation model directly in your system using this QGIS plugins. You can also download the DEM model. Okay, right. So now in this era of AI and machine learning, as I told you, like the possibilities are plenty. You can use the the data that is available, the models that are available, the platforms. Okay, so you just have to basically frame a structure of process with the satellite data. I think you have a solution out of that one. Okay, of course, the help and the process or the workflow, all these things are available as I told you, like in the public domain, you can go through and you can frame your own processing models using the QGIS, or you can directly go independently to the platform and you can do it. Okay, so these are some of the complementary technologies that are now, I mean, emerging as a good alternative to the having this, this spatial data. But as I told you, like they are limited by different factors. Okay, right. So these are some of the emerging where I think the geospatial technologies will play an even bigger role. Especially now the device, especially the mobile platforms, are now getting more involved in the capturing of the data, the processing, and also the dissemination of the data. So we can look forward to a very promising role of these handheld devices, mobile phones, or it could be any other handheld devices with the proper connectivity and all those things. That will play a very important role in the processing, collection, and also the dissemination of the geospatial data or the location-based data. Okay, fine then. So I'll summarize. I'll conclude here. So as I told you, like remote sensing platform is unmatched in many ways as compared to other platform. But again, you need to understand some of its limitations also. Especially, it will give you the print of the surface of the Earth. But when you need to add to that, data. You need to add to the data by doing a proper interpretation, proper processing, and also proper, field data. You need to validate that one, and then you can prepare a very, reliable, information or maps or GIS layers based on that. That will be very helpful for whatever mapping you're doing, modeling you're doing, analysis you're doing, or you want to derive some information out of that one. It is very helpful. Okay. So the other complementary technologies are also catching up. They'll only complement, they'll supplement to the satellite imagery. But again, the satellite imagery is the primary source of information that is needed for all our, remote sensing based data processing is concerned, right? So some of the applications, as I've told you, like are dependent on the satellite imagery for their effective planning, management, and also the critical decision making. So I think some of the examples you will come across during this particular training program. So that's it from my side. Thank you for your patient listening. Yeah, so I'll conclude here. So if there are any quick queries, probably we'll take. Otherwise, if you have a dedicated session, I'll try to answer in that particular forum. Over to you, sir. Chaitanya Gar.
Yes, thank you, sir. Thank you for delivering a very informative session. We have a few questions in the chat box. I would like to request the participants if they can unmute themselves and they can pose the question. Let me. There is one question on whether there is any satellite similar to GRACE in the chat box. I think GRACE follow-up mission is there.
Yeah, to my information, I think there's a follow-up mission to the GRACE.
Yeah, participants can now unmute themselves and they can pose any question. If they have any query, they can type in the chat box or they can ask it by raising hand and unmuting themselves.
Hello.
Yes, sir.
Good morning. Good afternoon. Is SAR satellite is polar synchronous or geostationary?
No, sir. Actually, it is not geostationary. Probably it is not sun synchronous also, because the need does not arise for a SAR data to operate in that polar sun synchronous. Mostly it will be like it may be a polar orbit that it will either go from north to south or it will go from south to north, because that is it will give you a programmatic acquisition of the data. If you are moving from north to south or south to north, so you'll have each and every track of the path that is traced by the spacecraft. But if you're putting it in geosynchronous, again, let's from an hypothetical point of view, we need to have a very high source of energy lot of energy is needed to pump that energy towards this, the Earth's surface from such an high altitude. So it is very, what you call, impractical to operate a SAR from a geostationary platform. But from a 4R platform, as like your remote sensing satellites, it can operate, but it need not be sun synchronous. Yeah, so I think to your question, probably.
Sir, what is LBS and OGC? Initially, you have shown some
Yeah, so
slides.
LBS is LBS is location-based services. So now, like we are using this location information. No? So the location information is used for providing a lot of services, whether it is like this. You are aware, no? Like you can ask for a transport service. You can book your what do you call this, groceries and all those things. So these are some of the location-based services which the whoever is providing you the services, the company or the organization, like they will use the location to deliver the services. So LBS stands for the location-based services, which in turn will use the navigation system, either the terrestrial navigation, what you get from your mobile devices, basically the navigation because of the your mobile towers. Okay, so the mobile towers will triangulate your location, and it will give the locational information to that particular what you call application app, we call it, no? So based on the app, whatever the service you selected, that will be offered. And OGC stand for the Open Geospatial Consortium. So probably I have not highlighted in that particular slide. So this is a consortium that is like the government agencies are there, the industry is there, the academia is there. So they all get together to to check out what are the policies and what are the specifications of using this geospatial data. Okay. So what specifications it should have, what policies have to be, what policies have to be provided so that the user community benefits from such policies and specifications. So OGC stands for Open Geospatial Consortium. So it's a body. It's an it's called it's a technical body that is involved in framing, as I've told you, like the specs. So because now the GIS data is also in terms of volume is growing very rapidly. So unless so, what is the advantage if you ask me? So this will help us accessibility of the data. That means we can access the data very easily. We can share the data, the interoperability. Like if you're working in QGIS or ArcGIS or any other licensed or open source software. So because it is OGC, we call them as OGC compliant. So if it is an OGC compliant, the chances, the possibilities of you using the data and openly, freely, and with the same, what you call authority and the flexibility, that remains the same for all the users. Okay. Yeah. So that is probably the point, probably in the net of scheme of things I forgot to focus on. But anyway, you have raised, it is very nice.
Sir, one small question. I'm
Yes, sir.
sorry. This is my third question. Is there any satellite which is made in India? I mean, produced in India or data generated in India related to groundwater resources?
So actually, whatever the sensors we are using are basically indigenous only, sir. Whatever the cameras that we are using for the imagery and also the other instruments are indigenous only. For the groundwater, because this is a groundwater phenomena, from the optical data, you cannot directly infer like what is happening beneath. So like whatever the grace you have tell probably is one spacecraft which is looking not only at the our country but is looking globally like what is the groundwater like subsurface phenomena. So you can only do a proxy from this multispectral satellite data as far as the groundwater is concerned. So on a like a proxy, that means not directly. So based on certain features, like based on the linear means or the filters or the catchments, you can estimate to an extent like what is the groundwater availability and all these things. So our satellites are indigenous only, sir. So probably in the context in which you have asked this question,
I think he want to ask if there is any satellite like GRACE. GRACE is something that does sensing of change in the gravitational potential. But as sir explained, if you want to make use of optical remote sensing for groundwater related applications, there is no direct way, but you can associate with lithology, mapping lithology, and other proxy features in the multispectral imagery. There is no other way.
Thank you, sir.
Any
Sir,
other query?
Sir, good afternoon, sir.
Please go
Yes, sir,
ahead.
please.
Okay, sir. My name is B. Santosh Kumar, sir. My question is that is there any possibility to download and create the contours from the Bunidhi?
Actually, directly contours. I have to
No,
check,
no,
sir.
wait,
Yeah.
Can
No,
we download the any
Yeah,
area of the map?
yeah, we can download any region of our subcontinent from the Bunidhi, sir. But before you download, it will tell you like what all the data sets are available. Actually, it's a query-based portal, sir. Probably to just brief you, it's a query-based portal. So just like how you, go to any, data ordering portal, you mention like between which dates you want to see the satellite image. First, you need to mention your area of interest. So once you mention your area of interest, then you have to mention like what type of data you want, whether you want multispectral data, whether you want a SAR data, or whether you want of different spatial resolutions. So all these things, it's an interactive portal where you have to give your inputs. So based on the inputs, it will tell you what all the data sets are available for a particular duration. That means from to to date. So based on that, you can select this, the data that you want to download. But again, some small registration, some other formality documentation is needed. So once you are through, on a given day, I think you can download up to some limit is there. I'm not exactly sure of the limit. So up to 5 meter data that is available for free. All this data can be downloaded free of cost. So it's an interactive portal, sir. Kindly go there, visit there. You can go through that portal and try to download the data.
Okay, sir. Because of we are came from the water resource department, we have the fine of the TTs. We have to provide some catchment area maps and the delineations and the flat flow canals. That is why we are taking that much of interest to take the maps for that Bunidhi or any, because it is the 10 meter, 5 meters resolution. We have to provide at least 10 meters or 15 meters or 20 meters contour interval.
Yes, sir. I mean, even the contour data is also made available. Because once you have the DEM or the DGM, you can generate the DTM. But like if you are looking for specific geospatial thematic layers, like related to water resources, you can also visit our Bhuvan portal, sir. So there already like geospatial information in terms of a particular resource. Like a lot of water resources layers are also there, so you can visualize based on your requirement what type of different water resource layers are there. You can look into that one, sir. Even our Bhuvan Geo portal. You can
thank you, sir. No. Thank you, sir. Last year I attended the 3 days Bhuvan portal. I am very appreciated because I delineate the catchment areas from the Bhuvan portal also, from the water resources information system, and that is also coincidence with the already we have the old maps.
Okay.
So we are also thankful to the NRSC Hyderabad providing the online sessions of the Bhuvan 3 days courses. Thank you.
Sure, sir. You're most welcome, sir.
Okay.
We will be providing a PDF of this presentation as well as the recording of the presentation will be uploading in the e-learning portal. So many people are asking in the chat box about presentation. There is one question on which one is better, ArcGIS or QGIS. Like, proprietary software will have its own advantages like ArcGIS, but you cannot work with ArcGIS on anywhere on any system. QGIS for beginner, I think for those who are at beginning or intermediate stage, QGIS has all the tools which you will find on ArcGIS. You can very well use QGIS for all the purposes. So there is
Yes,
one
sir.
question on what is the maximum vertical elevation accuracy that can be achieved using satellite?
Yeah, actually it differs. Value that can be, because it is dependent on various factors, especially the terrain. Like on a plain terrain, if you're imaging, I mean, if you're doing a lot of photogrammetric based analysis of that particular area, if you're collecting the elevation model, you will get reasonable accuracy. But in a highly undulating terrain, it basically varies with a lot of factors. And especially if you're looking at a pixel size of course of 30 meters, generally your accuracy also will equally affected by that one. Okay. So it is not, it is not consistent across the terrain. It varies. So you need to keep your application in mind and then go about using a particular elevation model. So, I mean, we cannot share for sure, like this will be the accuracy and that will remain throughout that particular area of interest. So it generally varies. So this is probably my understanding of the particular, the accuracy of DEM is concerned.
And if you want to achieve higher vertical accuracy, you can go for LIDAR survey of any limited for a limited area. You can conduct a LIDAR survey and you can prepare a DEM. Open access DEMs like SRTM, CartoDEM, they have I think vertical accuracy in range of a few meters, 1 or 2 meters.
Yeah.
So it depends on the application. If you are going for inundation mapping, you may need higher vertical accuracy. If it is only for basin delineation, you can make use of these open access DEMs. Sir, is there any India-based satellite or program like GF2 capable of detecting black and odorous water bodies? I think he is talking about water quality aspect.
Yes, sir. Actually, no, he is asking about the satellite program. That is a national, anyway, under NHP, I think probably we have some initiatives that were taken, especially the, mapping of the water resources or the quality of water resources is concerned. But like your attributes, especially black and odorous water bodies, whether, these attributes are a part of that, studies or the initiatives. So probably I'm not aware, sir. Probably you can throw a little bit of light. But yes, there is a national level project, the National Hydrology Project that was initiated to look at, look at our water resources in a more, scientific and a systematic manner using the satellite imagery. So that project we have initiated long back, and it's already, I think the second phase is going on, sir. So to my knowledge, probably you can throw some light, sir. Chaitanya Gar.
I think water quality aspect from to remote sensing, satellite remote sensing, it has many limitations. Like only optically sensitive parameters can be sensed. All the sediment content, maybe chlorophyll can also be mapped. There are we will be covering these topics, like we will be covering band indices like NDVI, NDWI. There is one NDTI for turbidity, NDCI for mapping of chlorophyll in water bodies. Like if there is incidence of high eutrophication, that can be mapped, but from satellite remote sensing, mapping of whatever use order is, I don't think it is possible.
Yeah.
But yeah, few water quality parameters can be mapped, and they can be associated with other parameters. But it has many limitations. Sir, what is the temporal resolution of Cartosat 3? There is a query.
Yeah, it is.
Yeah.
It is approximately 5 days, sir. I mean, probably
Temporal
for every
resolution.
5 days, yeah, temporal resolution. The frequency is every 5 days. Sorry, the temporal resolution, no?
Yeah.
Yeah.
Is
So
there any? Yeah, you can answer it,
Yeah,
sir.
it is correct. Sorry. I mean, sorry, it is for between 9 to 10 days. Yes.
Is there any standardized document for generation of contour data from SRTM? We will be covering this part.
Yeah, I think yes.
Yeah, we will be covering this during the training program. There are tools in QGIS for generation of contours if you give DEM as an input. I will request all the participants who don't have the queries, they can mute, and only those who want to ask anything, they can.
Good afternoon, sir.
Yeah, please
Yes,
go ahead.
Sir, you said there's a temporal resolution of 5 days for Cartosat 3, but we are getting months-old imagery on Cartosat. We registered as a government entity on the portal, but still we are getting months-old imagery only.
On
no,
Bunidhi.
sir, especially
On Bhunidhi, sir.
yeah. So especially during the monsoon season, no, sir. So this may be a small, what you call
Yes, the
delays
images
there
are
because of cloud cover.
pre-monsoon only. There's no post-monsoon or during monsoon images.
Yeah, probably can check with our people, sir. Like, because if your demand is like to have an access of the, very latest data, you can just put a query to them. What they do, sir, actually now, because everything is on the online portal, they will try to prioritize, certain areas. And so again, there is a, demand-based, what you call data availability also for some of the users. So probably if you can give your feedback that what is your case of using the satellite data, what is the urgency and all those things, I think they'll definitely get back to you with that
Okay, sir.
image.
Thank you, sir.
Yeah.
There are few more queries in the chat box. Does atmospheric windows are used for active remote sensing? I think answer is passive remote sensing.
Yeah.
For active remote sensing, the radar, it means you don't require atmospheric windows.
Yeah, that I think probably if you go through the slides, it will give you a clear, a picture of where these, microwave regions are used, especially for which frequencies and which energy wavelength regions are used. So based on that, you can understand like which frequency is used for a particular satellite. Okay. So now the NISAR mission is also, I think the announcement of opportunities is already announced. Already a lot of scientific project teams are formed. So it's a dual band frequency. It works on S and X frequency. So that means it has dual frequencies of 5 gigahertz and 10 gigahertz. So we are imaging the terrain in both these frequencies to have a better, what you call the collection of the imagery. So we can look at in detail, like what are the various terrain properties of the surfaces in the this microwave region.
Can remote sensing help to assess evaporation and sedimentation in reservoirs? As evaporation, not through direct means, but through energy balance, you can get an estimate of even actual evapotranspiration. There are data sets, open access data sets from MODIS, from vapor, that is FAO, and also I think under NHP, NRSC also has developed one product of evaporation. Sedimentation, you can you can assess the sedimentation in the live storage part by drawing the contours, like depending on the water level, you can get the water line, and then you can assess to trapezoidal formula what has been the sedimentation that has taken place in the over a time period. For that, you need to know the water level data from the project, from the reservoir authorities, and then you can map the water extent, and you see the change in the water extent to assess the sedimentation. Sir, would you like to add anything?
Yeah, probably I think you are the domain person in that particular area, sir. Yes, studies are there. We were using satellite imagery, so we can approximate to an extent. But again, with respect to the ground information, like whatever the sensors, ground-based sensors are there, we can validate to an extent, and we can prepare certain maps. So it is a scientific study of these aspects, the evapotranspiration and all those things, where the satellite data or the imagery is predominantly used.
There is a query on how can we measure the quantity of water flowing from a river into ocean during monsoon and post-monsoon. Again, there is one topic, there is one aspect called satellite altimetry. You can get water level using altimeters, but for that, I think you need to, the river channel should not be very narrow. And also, it depends on when you have the satellite pass. Only then you will get the water level. And based on water level, if you have any stage discharge curve for that particular virtual gauge station, you can assess you can get an estimate of discharge. But nowadays, we had one mission called SWOT, SWOT, which gives, I think, an estimate of discharge. It is still the scientific products are not publicly available. There, it is still under research. Sir, you may if you may add to it.
Yeah, I mean, it can be approximated, sir. Probably a very accurate, understanding of the quantum of water may be difficult, especially from the satellite imagery. But like you told, using the ground-based instrumentation, telemetry. So I think to an extent, our CWC is doing that. Wherever there are water gauges, telemetry is available that can estimate, from the rainfall data from the IMD. So all these things, I think the models are being created that can estimate. So such information is available probably at at an experimental stage, especially when it comes to quantifying the volume. But yes, it would be a very interesting and very potential case if we can estimate such discharges or the flow or the volume from the satellite data and also the ground-based measurements. So it will be a very interesting project to study.
I think there are many queries in the chat
Yeah,
box, but we have a limited time.
Yeah, mining industry. Probably if you ask me at the moment, now the drone and the UAVs are mostly used, sir. Satellite imagery, because due to their limitation of repeativity, again the cloud cover, especially the optical data. So they are used, but mostly now with the new regulations and the policies of the mining is concerned. Now each and every what do you call this contractor is now he has to use the drone imagery, process the data and derive the whatever the outputs are there with respect to the what you call the material that is being mined and the what do you call the, probably I'm not aware of that mining terminology. So all these things have to be prepared, or probably they have it weekly, so not weekly, but over a period of month or in a thrice a month. So they need to submit these reports to the the concerned authority. So yes, remote sensing is used, but especially the drone data and the UAV based platforms are used for capturing this data. Yes, satellite imagery we can also use, but again, as you have seen, like we need to see whether a particular pass is there over that region, or do we have the historical data of that particular area from the satellite platform. So all these things need to be verified, and you can use in conjunction with the whatever the drone or the UAV data that is being collected. Satellite imagery is used for mapping of particular regions. Okay, so if you want to do a mineral mapping or a lithological mapping, or the if you want to quantify different types of many minerals in that particular area, so that is where you use the satellite imagery. But when it comes to the mining industry, I think now it is the drone data, drone platform is mostly used. Yeah, you can check the nitty-gritty, sir. Probably I cannot answer each and every related to the Bunidhi. So I'll just mention in the stage, but you can write to me for any feedback from yours directly to my mail. You have my mail in that presentation. So any specific related to the query, I'll try to share the and a team who is looking after the Bunidhi. But definitely we will take your feedback from this platform also. Yeah, I mean, the possibilities, so I've only shown you probably through this training program, the possibilities of using the satellite data. But how you want to use it, probably if you explore a little bit, you can also definitely find, a way ahead of how it can be used. So any technical help that you need related to the soil, agriculture, forestry, probably you can write to me. I'll try to, I'll try to reply to you, or I'll try to take the help of our people here who are working specifically on these domains, so that you will also clarify your doubts before you proceed with the particular study of using the satellite imagery. Okay, sir.
Yeah.
Back to you, sir.
Yeah, thank you. Thank you very much. I would like to inform participants that we will be having the second session on basics of geographical information systems, including map projections at 3 o'clock. You may join using the same link. We will be joining this meeting again at 3 o'clock. On behalf of National Water Academy, I thank Shri Harish for delivering this session on introduction or basics of remote sensing. We will be sharing the recording as well as the presentation. We will be uploading in the evening. So we will meet you again at 3 o'clock. Thank you.
Yeah. Thank you, sir. Thank you.